Right now, in the driest desert on Earth, a telescope has just spotted something that shouldn't be there. And it's not alone. This machine has already found enough to prove our solar system looks different from the one we thought we knew. Because what this instrument has found in barely a year of testing is not one discovery. It is a flood of them. Two worlds sitting 1,000 times farther from the Sun than Earth. 11 hidden companions locked into Jupiter's orbit that nobody had ever counted. More new asteroids in a year and a half than humanity found in the previous 3 decades combined. And inside one of its very first test images, a cluster of stars so dense that individual points had never been separated from each other before. This is the story of how the Vera Rubin Observatory is redrawing our solar system in real time, and it did most of this before its real mission had even started. My name is Dr. Bernhard Kessler, and this channel is where we dig into stories like this one, the real discoveries, straight from the source. If that's your thing, the subscribe button is right there, and it genuinely helps this content reach more people who care about the science. Let's get into it. The story doesn't start with a headline. It starts with a routine data dump, engineers checking whether the software actually works before the real mission begins. To understand why that matters, you have to understand how astronomers even find something this far away in the first place. An object at the edge of our solar system doesn't announce itself. It doesn't glow. It reflects a tiny sliver of sunlight from a sun that, at that distance, looks barely brighter than any other star in the sky. The only way to catch it is to photograph the same patch of sky more than once and watch for a single point of light that has quietly shifted position while everything else around it stayed still. Even then, one detection isn't enough. Astronomers need several separate sightings spread across days or weeks before they can calculate even a rough orbit, and until that orbit is confirmed, the object only carries a provisional name, a placeholder that stays attached to it for months or sometimes years. That's exactly the process this telescope had to prove it could handle, and even in its earliest, unfinished testing phase, it found 380 previously unknown objects orbiting beyond Neptune. 2 of them stood out immediately, provisionally named 2025 LS2 and 2025 MX348. Both sit on orbits so stretched out that at their farthest point, they're roughly 1,000 times farther from the Sun than Earth is. That's enough to place them among the 30 most distant known objects in the entire solar system. For comparison, Pluto, the thing most people picture as the edge, reaches only about 49 times Earth's distance from the Sun at its farthest point. These 2 objects are roughly 20 times farther out than that. If Pluto's orbit were the size of a dinner plate, these 2 would be sitting in the parking lot outside. Here's why that detail matters beyond the raw distance. Objects with orbits this extreme are exactly the kind of clue astronomers have been chasing for years, evidence of something massive out there. Something whose gravity could bend and stretch orbits into shapes like this in the first place. A handful of these extreme objects have been found before, one at a time, over decades of painstaking searching, using telescopes that could only stare at one small patch of sky for a single night before moving on to something else entirely. Every one of those earlier finds has been used to argue about whether something large and undiscovered is quietly shepherding them from the shadows, something nobody has ever directly seen. 2 new data points might not sound like much on their own, but the entire known population of objects this extreme has, until now, consisted of only a handful of cases, collected across generations of astronomers working with very different instruments. Every new one shifts the statistics in a meaningful way. And this was just a test run. The real 10-year mission hadn't even properly started yet. This came out of commissioning data, the equivalent of a telescope clearing its throat before it actually starts talking. If two test objects can already move the conversation about the far edge of our solar system, what happens once this telescope repeats that same observation over and over every few nights for the next 10 years? To understand that, we need to look at what else was hiding in that exact same batch of data. And this one has nothing to do with the outer solar system. It's about something orbiting right next to us, on the doorstep of the largest planet in our solar system that we somehow never finished counting. Jupiter isn't alone on its orbit around the Sun. There are 2 points, sitting 60 degrees ahead of the planet and 60 degrees behind it, where the combined gravity of the Sun and Jupiter balances so precisely that objects can sit there, essentially motionless relative to the planet, for billions of years without ever drifting away. These points are called Lagrange points, and the objects trapped inside them are known as Jupiter Trojans. Scientists believe these Trojans aren't leftovers from some later era. They're thought to be relics from the earliest, most chaotic period of the solar system's formation, captured before the giant planets had even settled into the orbits they hold today. Some models suggest they were pulled in during a period when Jupiter and Saturn briefly shifted position, dragging debris into these stable pockets almost by accident. That makes each one, in a very real sense, a fossil. Not a fossil of life, but a fossil of motion. A frozen record of what our solar system's architecture looked like 4.5 billion years ago, before anything we recognize today existed. Finding new Trojans has traditionally been slow, painstaking work because they sit at a fixed angular distance from Jupiter and require exactly the right patch of sky, photographed at exactly the right time of year, to catch them at all. Most surveys before this one weren't wide enough or didn't return often enough to catch more than a handful in a given season. Here's where it gets remarkable. In a single small patch of sky that this telescope observed during its testing phase, not a dedicated Trojan hunt, just one ordinary slice of a routine test, 11 new Trojans turned up. 11, from a tiny fraction of the sky the camera can cover in a matter of seconds. That same test image also contained more than 2,100 previously unknown asteroids in total. 7 of them pass close to Earth. 9 more sit out beyond Neptune, alongside the extreme objects we just covered. That wasn't a lucky hit on a rare target. That was one single sample, revealing just how much of our own cosmic backyard has simply been sitting there, invisible, this entire time. Not because these objects are unusually small, and not because they're unusually far away. Jupiter's orbit is practically next door in cosmic terms, but because no instrument before this one could scan wide enough and return to the same patch of sky often enough to reliably tell the difference between a point of light and a point of light that has moved. Picture it concretely. You photograph the same section of night sky twice, a few nights apart. Almost everything in the frame looks completely identical. The same stars, in the same positions, glowing the same brightness. But a handful of dots have shifted, even if just slightly. That shift is the entire difference between a star that has occupied the same spot in the sky for thousands of years and a rock that has been silently orbiting the sun for billions of years without a single human being ever noticing it was there. 11 Trojans and over 2,100 asteroids from one single test image is already remarkable, but it's still just one patch of sky, captured during a phase when the telescope wasn't even fully operational yet. What happens when that exact same method gets pointed at the entire southern sky night after night, for a year and a half straight, without stopping. This is where an already impressive number turns into one that's genuinely difficult to hold in your head. Over roughly 18 months, most of it before the real official 10-year mission had even begun, this telescope's team found nearly 12,700 asteroids. To put that in context, humanity spent the previous 3 decades cataloging about 5,000 known objects beyond Neptune. Total, 3 decades of dedicated surveys, specialized telescopes, and painstaking follow-up work from teams all around the world, working with instruments that had to be pointed carefully and deliberately at one small region at a time. This telescope's early data set alone already contains 380 of those distant worlds, submitted in a single batch to the International Astronomical Union's Minor Planet Center, the official body that verifies and catalogs every new object found anywhere in our solar system, and without whose confirmation, no discovery officially counts. And again, all of this came before the mission had officially started. One scientist involved in the analysis described the search like this: finding a single one of these distant objects is like searching for a needle in a field of haystacks. Out of millions of flickering points of light scattered across every image, a computer has to sift through billions of possible combinations of motion and brightness to identify the handful that are genuinely real, distant worlds, and not just noise, a cosmic ray hitting the sensor, or a satellite drifting through the frame at exactly the wrong moment. That's really the point buried in all of this. It's not simply that this telescope finds a lot of things, it's the rate at which it finds them. What older surveys pieced together painstakingly, one object at a time, over the course of decades, this instrument accomplished in a year and a half. And that year and a half was technically still just a test. Think of it less like a photograph and more like a census that updates itself while you're watching. Not a single snapshot you take once and rely on for the next 30 years, but one that refreshes every few nights, all on its own, without anyone having to request it. Objects that were completely unknown last week already have a provisional name, a rough calculated orbit, and a permanent place in an international database today, this week. And that has a consequence that's easy to miss. The solar system map most of us learned in school, 8 planets, a modest handful of moons, a few thousand cataloged smaller objects scattered between them, isn't just getting outdated. It was already out of date before this telescope's real, decade-long mission had even properly started. The map is being redrawn in real time, and most of us haven't even noticed the ink is still wet. What's still missing from this story is something that isn't about motion or distance at all. It's about detail, about finally being able to see something that has been sitting motionless in the same spot in the sky for billions of years. In a way, nobody has ever managed to see it before. Not every discovery in this story is about something moving through the dark. Some of it is about seeing something that's been sitting perfectly still the entire time, only now in far greater detail than anyone ever managed before. Among the very first test images released from this telescope was a globular cluster called NGC 6544, a tightly packed, roughly spherical swarm of stars sitting about 8,000 light-years away, bound together by its own gravity for billions of years. Clusters like this have been photographed for well over a century, going back to some of the earliest astronomical surveys ever conducted. But in this telescope's image, individual stars near the dense, crowded core. Stars that every previous generation of telescope simply blurred together into a single indistinct smear of light, separated out into tens of thousands of individually visible points. That distinction matters for reasons beyond how striking the image looks. The more individual stars you can pick apart inside a cluster like this, the more precisely astronomers can measure its overall structure, estimate its age, and map how its stars are distributed by mass, from the smallest, faintest members all the way up to the largest, brightest ones. Globular clusters are among the oldest intact structures anywhere in our galaxy, effectively fossils from the earliest chapters of the Milky Way's history, largely unchanged since long before our own sun ever formed. Being able to count their stars individually, one by one, instead of averaging a single blurry smudge of light, hands astronomers a dramatically sharper tool for reconstructing exactly how our galaxy came together in the first place, layer by layer. And here's the detail that ties this whole story together. This came from a single test image, not from years of dedicated observing time pointed carefully at one specific target, the way earlier detailed studies of clusters like this one were conducted, but from the exact same wide, sweeping pass across the sky that, in that very same run, also turned up the extreme distant worlds and the hidden Trojans we covered earlier. One pass of the camera, one night, more or less, and it delivered both a fresh census of moving rocks scattered across our own solar system and a level of resolved detail on an 8,000 light-year-old star cluster that older, purpose-built instruments simply couldn't reach, even after being pointed at that exact same target for far longer. That's the real signature of what makes this telescope different from everything that came before it. It isn't a specialist. It doesn't have to choose between hunting asteroids and studying ancient star clusters. It does both simultaneously in the same exposure, without slowing down for either one. One more piece of this story belongs on the table before we wrap up, because it explains why this particular telescope exists at all, and carries the name that it does. It's named after Vera Rubin, an American astronomer whose measurements of galaxy rotation back in the 1970s produced some of the strongest early evidence for what we now call dark matter, mass we still can't observe directly through any telescope, only detect indirectly, through the gravitational effects it has on everything around it. Working alongside astronomer Kent Ford, she found that stars near the outer edges of galaxies were moving just as fast as stars much closer to the center, which shouldn't have been possible under the physics known at the time, unless there was far more unseen mass out there than anyone had accounted for. It took years for the wider scientific community to accept what her data was showing. She died in 2016. It wasn't until 2020 that this telescope, still under construction at the time, was formally named in her honor. And it wasn't until 2025, 9 years after her death, that it captured its very first image. Now, that same telescope is hunting, systematically and at an enormous scale, for exactly the kind of invisible structure she was among the first to prove was real. Not as a footnote to its mission, but as one of its central goals for the next 10 years. So here's the full picture. One more time, in roughly 18 months, most of it before the real 10-year mission had even officially begun, this telescope found two worlds sitting 1,000 times farther from the Sun than Earth, pushing the boundaries of what we know about the outer edge of our solar system. It uncovered 11 Jupiter Trojans and over 2,100 previously unknown asteroids from a single test image. It cataloged nearly 12,700 new asteroids in total, more than the entire rest of humanity managed to find in the 3 decades before it. And in that same stretch of testing, it resolved a star cluster in a level of detail that dedicated specialized instruments hadn't achieved even after being pointed at it for years. The real 10-year mission has only just started. If the test phase alone produced all of this, what's going to be sitting in that database 3 years from now? What's going to count as known by year 8, that right now, tonight, nobody has found yet? Tell me in the comments which of these hit you hardest. The distant worlds at the edge of everything, the hidden Trojans nobody had counted, the sheer pace of discovery, or the star cluster resolved in a way no telescope had managed before. And if this kind of fact-checked space story is what you're here for, subscribe. There's a lot more coming on this telescope.